Okay, here we are in a brand new video, and it's about a proof for Pythagorean Theorem. As far as I know, it doesn't exist anywhere except in this video, which is a better version of the video just before this. This is video 4. The last one was video 3. So it's about a diagram that I want to credit. The diagram was in a book that was published first in 1926. And the only description of that diagram was that it was so self-explanatory that it did not need any further explanation. That's basically what they said about it. They didn't say where they got the diagram from, and I've not been able to determine where it came from. And I didn't learn anything about it because they had that comment. That was the only thing about it in the whole book. Okay, so I don't really agree with them. I think that this is the basis for a proof of the Pythagorean theorem that's not been seen before. So that's what this video is about. So on the left hand side, that book's title, well, it was printed first in 1926, and the title of it was Mathematics for Engineers. It was by Dull and Dull, and it was published by McGrawHill. Okay, so moving on. And I have only 10 minutes, so I have to really hurry. And I'm going to take a few shortcuts, and I'll apologize for them now. You'll see what they are as we go along. On the left-hand side is the diagram. It's been programmed to be interactive. Okay, so let's see what that looks like. Here's a angle control. Okay, you can see the angle has changed. Now, I claim that this is a mathematically accurate model. Let's see what that looks like. If I measure the length of this line segment, A sub 1, put that number in a calculator and multiply it times itself, it'll be exactly equal to the length of this green line segment. If I take this B1 and measure it, multiply it by itself in a calculator, it'll be exactly equal to the length of this blue line segment. So I represent that this is a mathematically accurate model, and that it uses, instead of numeric values, it uses symbolic values. Okay, so I'm going to show why. This has some curious labeling on it. It looks like well, a squared plus b squared is equal to c squared. In the special case that c equals 1, then 1 is equal to c squared, and we can say that a squared plus b squared equals 1, or a squared plus b squared equals c squared. Anyway, this is a unit circle, so between the center of this circle and the outside of this circle is 1. It's like an invariant. That's a new term. It just means that the sum of these two terms is invariantly equal to 1. In other words, it never varies. The sum is always 1. The sum is a constant. That's what invariance means. It never changes. The sum never changes. It always equals 1. Okay, so moving on, I'm going to move over here to full screen in order to be able to develop a framework that will allow the rest of this discussion to unfold. And I normally don't draw this stuff, but I have to do this in 10 minutes, and I can't seem to do it another 16 or 18 minutes. Hopefully if I draw this stuff first, I'll be able to do that. I have a right triangle here. It's A, B, and C, but if C equals 1, then C equals C squared, because 1 squared is still 1. Okay, I'm going to move on here. If I draw in a altitude for this triangle, if I choose this to be the base of this triangle, this would be the altitude to it, which means there's a right angle here. If this is where I choose to put my angle theta, then this will be 90 minus theta. and this will be theta. That'll make this theta, and you can pause the video as long as you want to be able to satisfy yourself for that. But you'll see that that makes all of these self-similar triangles. Because all the angles in each one of these are the same. They're self-similar. That's a term from fractals, which we'll get into the next video. I have 3 similar triangles here. And from geometry, for self-triangles, the ratio of corresponding sides for the largest triangle equals the ratio of same corresponding sides for the smallest triangle. Okay, so let's look and see what that'll look like. And I claim that there's something special going on here worth taking note of and keeping track of. This side right here is the hypotenuse of this smallest triangle. So let's look and see where that would fit inside of this framework here. The hypotenuse, so the hypotenuse of the smallest triangle would go here, and we can see that symbolic value for that is B. And so the thing that's going on special with this side is it also is, and I'm going to draw this with a thin line. For this biggest triangle, that's the opposite side of the biggest triangle. So let's see what that would look like in this framework here. So the opposite side of the largest triangle goes here, and it's also B. So when we cross multiply, we get a B squared term. Now everybody knows, and I'm going to have to go fast here, for the hypotenuse for the largest, hypotenuse for the largest triangle goes here, and we can see that's 1. So we put a 1 here. Now if we look here, this piece right here is the opposite side of the smallest triangle. Well, let's see what that looks like. Here's the smallest triangle, and there is the opposite side, and it doesn't have any symbolism for it. So I'm just going to choose the symbol E to represent the distance across these 2 reference points, and I'm going to put that right here. So that's equal to E times cross multiply E times 1. So this being equal to this, I can write either one of these right here. So this symbolism, B squared, represents the length of this line segment. And this is why. Okay, moving on. Over here, the ratio for corresponding sides, when we're talking about a ratio of adjacent sides to hypotenuses for the largest triangle, and this same for the medium-sized triangle, go over here in this framework, right here. So I'm going to use a different color. So the adjacent side for the largest triangle, let's see what that looks like. Here's the largest triangle, and the adjacent side of our angle for the largest triangle is right here, and that's A, and that goes right here. So that's A. It's the adjacent side of the largest triangle. Okay, so anyway, moving on. Now what we're looking for is what goes right here. That is the hypotenuse of the medium-sized triangle. Okay, well, so I'm going to highlight the medium-sized triangle with a little bit heavier markings. Okay, here's the medium-sized triangle. Now, this is the hypotenuse of the medium-sized triangle. And so let's look and see. Well, we've already got that there. No. Okay, that's what we're looking for. We're looking for the hypotenuse of the medium-sized triangle, and it's right here. So what's its value? Its symbolic value is A. And that goes, so the hypotenuse of the medium-sized triangle goes here, and we see that that has a symbolic value of A. So when we cross multiply, we have A squared term. And everybody knows that the hypotenuse of the largest side is right here. So let's see that again. The hypotenuse of the largest triangle is right here, and that's equal to 1. So that goes right here. The hypotenuse of the largest side goes here. It's 1. So anyway, this side right here, what goes there is the adjacent side of the medium triangle. The adjacent side of the medium triangle goes here. See what that looks like. Okay, here's the medium-sized triangle, and I represented this is the the adjacent side of the medium-sized triangle. So it doesn't have a symbolic value, so I'll just invent one. D. We'll call it D. It measures the line segment length between these two reference points. Now, so that's, if we put that here and cross multiply, we have D times 1. And so we have D is equal to A squared. These being equal, I can put either one of these symbols right here, A squared. So we can see now why A squared plus B squared is equal to C, or C squared in a special case where C is 1, then it doesn't matter because 1 is equal to 1 times 1. Okay, so that's the end of this video. It's the proof of the Pythagorean Theorem. I haven't seen it anywhere. So thank you for watching. Please like and please subscribe. The first thing I'm going to do is escape from this full view, and then I'm going to go look and see what our time is. Oh, it's 12 minutes. I'm hoping that that'll work.